Hey, Calc students, this is Mr. Beck. Today we're going to be talking about Taylor series, Taylor series and Maclaurin series. Now, when it comes to Taylor and Maclaurin series, what these are really doing is we're taking 8.7, which we talked about Taylor polynomials. And then if you notice in 8.7, what I ended up doing with each one of my Taylor polynomials, I ended up writing it as a rule in the series notation. So really 8.10 is going to be a compilation of a lot of the sections 8.7, 8.8, and 8.9. Talk about a couple of details that it's really extended details beyond that, but a lot of the stuff we really should know. And we're going to put together in just a table of series, and we'll discuss the series because at this point we've worked with them enough, and today with the additional work we'll work with them enough that you should be able to recognize the series for what they are. So if you remember from 8.7, our Taylor series was f of c plus f prime of c times x minus c to the first over 1 factorial plus f double prime of c, x minus c to the second power over 2 factorial, generically calling it the nth derivative at c over n factorial times x minus c to the nth power, which is where we can put it all together into one overall series. Now, whether that series starts at n equals 0 or n equals 1 is going to be based off of the series, so we're always going to have to keep that in mind. If we look at this, there's no such thing as a 0th derivative, really, technically, but anyway, I shouldn't have said that, moving right along. But we have this Taylor series for our function at x equals c. And of course, if c equals 0, then we do have a Maclaurin series. So example number 1, we are asked to find the Maclaurin series, aka c equals 0 for cosine. This is something we should know pretty well because we've done it over and over and over again, but that's okay. It doesn't hurt to do it one more time. So we have f, find f prime, f double prime, f triple prime, fourth derivative. If I wanted to go fifth derivative, I totally could have. So f of 0, f prime 0, 0, f double prime, f triple prime, fourth derivative. And so what we're doing there is we're building our Maclaurin polynomial. So our Maclaurin polynomial is going to be 1 minus x squared over 2 factorial, and that's because we skipped that first degree term. We're going to skip the third degree term. The fourth degree term looks like this. We could follow the pattern at this point, hopefully. And we could write that as the sum. Now, if we say sum going from 0 to infinity, then what should happen is we're alternating, so -1 has to be taken to the nth power. Not n plus 1, nth power, because -1 to the 0 is +1. If we notice our exponents are going up by 2 each time, therefore we have x to the 2n, and then over 2n factorial. Doesn't hurt for us to double check. If n equals 1, then that's x squared over 2 factorial, which is what we're supposed to have. Then we want to find the interval of convergence. This is where we jump into 8.8. So in 8.8, we use the ratio test to find the interval of convergence. So we take the limit of the next term divided by the previous term. And if you remember, we started taking that divided by the previous term into multiplying by the reciprocal. Then we say that limit has to be less than 1. And remember, this is sort of modeling whatever our series is as a geometric ratio. And then we find the limit. So we simplify algebraically. And if we notice, we only have n's in the denominator. So we have x squared over infinity, which ends up being 0. So what that tells us is our radius of convergence is infinity, because that's always true. Therefore, we go from -infinity to infinity for our interval of convergence. And that is what we're looking for. Now, we should have seen this when it comes to cosine. Cosine interval of convergence is -infinity to infinity. That's something that we're going to need to know very, very soon and know it very well. When it comes to our second example, we're going to take the f of x as a sine of pi x. And once again, we're going to find the Maclaurin series. So we're going to center it at 0. The reason why we're centering it at 0 is because this is another one that you should know really, really well. Now, what's different is we have a pi. So let's go ahead and see how that affects things. We write down f, f prime, f double prime, f triple prime, and then the fourth derivative. And we're expecting that every even derivative and the original function itself has to be 0 because the sign is not a function. F prime is pi, f double prime is negative pi cubed. Fifth derivative, I'm sorry, that was triple prime. Fifth derivative is pi to the 5th power. So our Taylor polynomial, we are going to write as pi over 1 times x, pi negative pi cubed over 3 factorial x cubed. And if you notice, the pi and the x both have the same exponent, so we can generically write those together as pi x to the nth power over n factorial. pi x to the nth power n factorial. Let's go ahead and introduce the alternating so we can complete this. Alternating, should this be n or n plus 1? Well, in our first term, or if n equals 1, then we have a positive, so we need to say n plus 1, which is why we could go ahead and, I'm not sure why I did that, but it's one of those habits of mine. And then I shouldn't have said n, and let me go ahead and clarify. This would be 2n plus 1 because we're alternating by 2 each time. And the first term is going to be 1, so if n equals 0, and so on. Anyway, regardless, we brought it together into one big Taylor series. So we went from the Taylor polynomial to the Taylor series. Now, what's the interval of convergence? Because this is signed, my hope is at this point you know that the ratio or the radius of convergence is infinity. We could show that. It's honestly very, very similar to what we did right over here. When we take the next term to the previous term, we're going to have the series of n terms in the denominator. Let's highlight right there. And we're going to get our radius of convergence is infinity. So our interval is negative infinity to infinity. Again, very similar to the proof over here. If you have any questions, always feel free to ask me. Now, when it comes to convergence of a Taylor series, what I did was I wanted to bring back the Lagrange theorem, also known as Taylor's theorem. Taylor's theorem says that the remainder has to be less than the coefficient of the nth derivative, or the n plus 1 derivative, times the max value of the next derivative over the interval. So if that limit equals 0, then what that means is our function converges wherever the limit does equal 0, or the Taylor series converges if that limit of the remainder does equal 0. What does that mean? Well, let's kind of take a look at this in problem number 3. Let's find the Maclaurin series. Very, very big on the Maclaurin series today for our function e to the negative 3x. So let's first do that. We have f double prime, f triple prime, fourth derivative. I'm a little behind. Now, at this point, hopefully we could see a pattern here. So I also like to write the nth derivative. And we want to know that nth derivative just so that we can help establish a pattern. And honestly, it'll help when we prove that it's going to converge for all x. So with that said, f of 0, f double prime is 0, f double prime is 0, triple prime, fourth derivative, nth derivative. We can go ahead and build the Taylor polynomial out of that, or Maclaurin polynomial out of that. So it'd be f of 0, f prime over 1 factorial, f double prime over 2 factorial. And if you see, I started combining those together into one term. And that's how I'm going to build my overall a sub n for my series. And now with that series, if n equals 0, then I will have 1. Therefore, we're going to start from 0 and go on to infinity. Now I'll show it converges for all x, which means let's go ahead and find the radius first. So our radius, we use the ratio test one more time. And that ratio test does give us a limit of 0. So our interval of convergence is negative infinity to infinity. Now, should that be enough? Yes, but let's go ahead and show that Taylor's theorem when we find our remainder is going to be the coefficient of the next derivative, which is why I like to see this nth derivative, because then I can say what's the n plus 1 derivative. Now times the max value. Now this max value, honestly, we don't really need. And the reason why we don't really need for this case is because we want to show the limit of, as n approaches infinity equals 0. So really, this is what we want to know equals 0. Now, basically, the max value of that expression does equal 1. So multiplying it by 1 doesn't affect it. If it's anything other than 1, well, if you take 0 times the max value of, like, say, 100, you're still going to get 0. So we really don't need that max value component of it. What we do need to show is that this limit does equal 0. So if we take the limit of that, what I am envisioning, and I rewrote it so that it's x times 3 to the n plus 1. I guess that should have been x to the n plus 1 times 3 to the n plus 1 over n plus 1 factorial. Now, really, this limit should equal 0, and that's because the exponential does grow slower than the factorial does. Now, we talked about that. To really prove this limit 0, we should probably look at it as a series to say what's going on with the series. We could use L'Hopital's rule if we knew the derivative of a factorial. We don't officially know that, so L'Hopital's rule is sort of out right now. But in any case, since that limit is 0, we have convergence over the entire interval, and that entire interval is from negative infinity to infinity. So the whole idea of us going through this is this proved convergence. So moving right along, let's talk about power series in general. This is going to be a list of a lot of the power series that you are expected to know. And when I say expected to know, when I'm going to be giving you a quiz, I'm really going to say, hey, here are all the different series. Go ahead, write down, or here are all the different expressions, write down the series for each one of these expressions. So that's a tall order. So let's kind of hit it one by one and say, how are we supposed to remember all these different things? Well, the way that we're supposed to remember all these different things, one, if you remember the 1 over 1 plus x, that's how we began our discussion. We said, okay, that looks like the geometric ratio 1 over 1 minus negative x, which is where we built the Taylor series that we see right here. And we can generically write it as negative 1 to the n, x to the n. Now, our radius of convergence, the most important thing, our radius of convergence is 1. And since we did this as a geometric series, our radius of convergence should go from negative 1, or our interval convergence should go from negative 1 to positive 1. Now, not included, and the reason why it's not included here is because it's a geometric. I'm going to jump down to sine and cosine really quick, just because I've talked enough about it. At this point, we could redevelop the series if we wanted to. Most important thing is we start recognizing what that nth term is going to look like so that we can write it as a series. Now, the radius of convergence for both sine and cosine is from negative infinity to positive infinity, something that you are fully expected to know. If we go back to example number 3, we talked about e to the negative 3x, and we saw that the interval convergence for e was negative infinity to infinity as well. So keep in mind the interval convergence for e is infinity. So the radius of convergence for each of these is also infinity. Now, one of the things that I like about e, I think that we have seen this a couple times now, 1 plus x squared over 2 factorial, and so on and so forth. Now, if you remember, the derivative of e is e. So if I take the derivative of x, I'm going to get 1. The derivative of x squared over 2, I get x. And I can keep going with that. So fascinating thing. But if you don't remember the e power series right from the beginning, you can say, okay, let's start with 1 because e to the 0 is 1. Well, integrate that, you get x. Integrate that, you get x squared over 2 factorial. Integrate again and again and again, and you're going to get each one of the terms in the series. So that's a helpful reminder for you in case you don't remember exactly what that series is. My hope is you eventually remember that series. Then we come up to the two functions that we did in 8.9. Where in 8.9 we talked about different, I guess it was 8.8 still, we talked about differentiating and integrating functions. So to turn the natural log into a series, we differentiated it first, and after we differentiated it, we used this geometric idea to build the series that we see here. And that series is now centered at 1, and it ended up with a radius of convergence of 1. Now let's look at some details about the interval of convergence. The reason why it doesn't converge at 0 is because natural log has an asymptote at x equals 0. That's my really bad rough graph of that. So because of that, then we know that we don't have convergence at 0, even though the radius is 1. But if you remember, we integrated. So if we integrated, then our interval originally was from 0 to 2, but then we integrated it, which is where 2 ended up getting included on that interval of convergence. So because we integrated, we included the 2. And then you're going to see that with the arctangent one as well. I did give you some homework over the arctangent to kind of help bring about this overall power series. So when it comes to that power series, we want to be able to look at it and say we understand why it is what it is. The homework was hopefully designed to do that. Now, if you remember, we did the geometric ratio-ish idea. We said the interval of convergence was negative 1 to 1. But then when we integrated it, what will happen is we will include those endpoints. So the way that I remember these is, first of all, by the radius of convergence. Radius of convergence for e, sine, and cosine are negative infinity to infinity. The other ones, because this original one was a geometric ratio, it doesn't include it. When it comes to these two, it does include it because we integrated to get the Taylor expressions. I threw arcsine on here just because it's another common one. I'm not going to require you to know this one. The 1 plus x to the k power is what we call the binomial expansion. You guys remember this as n choose r times x to the n. So if you remember that from pre-calculus, that's how we come up with each of the individual terms. Well, if you remember, we had a formula for n choose r, which is n factorial over n minus r factorial times r factorial. Well, that's how we're building each of these individual expressions. Am I requiring you to remember that? No, because this isn't a stats class. However, it's very, very useful to know, and colleges honestly like to see that as well. Now, convergence or divergence at that point is going to be based off of whether we end up there as a alternating series at that point. Anyway, example number 4. So if I want to find the natural log of x plus 2 as a series, what I could do is I can go back to my natural log series. And in place of x, I could put the x plus 2. So my first term is x plus 2 minus 1. Second term, I'm just going to go ahead and simplify it as x plus 1 squared over 2, x plus 1 cubed over 3, et cetera, et cetera. We can build the series out of that. Now, as we build the series out of that, suddenly we shifted our center. Our center no longer is at 1, our center is at -1, which affects the interval of convergence. It's still not going to converge at -2 just because that's going to be the asymptote, but it does converge at 0. On example number 5, this looks like the 1 plus 1 over x. So if you notice, I rewrote the 1 plus 1 over x right here. But in place of the x, we have the square root of x. So we can go ahead, put the square root of x into each of the individual terms. And then how do we build the rule? First term is positive if we start at 0. And the first term doesn't have an x value. So then if you notice, that's going to be 1/2, 2/2, 3/2, 4/2, which is how we get the n over 2. Interval of convergence, this is straightforward from a geometric. So we'd say from -1 to 1, not included. But the domain of this, because we're working with the square root function, the domain is just going to be from 0 to infinity. So if we intersect those two, we include 0, since 0 is going to be included in that interval, and we end at 1 and we don't include that endpoint. So this is going to be a situation where you can't just memorize certain rules. You have to look at the domain, compare it to the intervals. To find 3 non-zero terms, this is where I start getting really fascinated by the idea of series. We can approximate that more complex expression by, let's multiply the E series by the square root of 1 plus x series. Now that square root of 1 plus x series was 1 plus x to the 1/2 power. So for that 1 plus x to the 1/2 power, my first term, let's go ahead and look up here. And I'm going to write this right here, 1 plus x to the 1/2 power. It's going to be 1 plus 1/2 x plus, this is going to be 1/2 times -1/2 over 2. So that's actually a -1/8 x squared. Now I can go further, but if I want just the first 3 non-zero terms, then what's going to happen is I'm just going to write down each of these and honestly FOIL. So I FOIL the 1, multiply those through. And then if I multiply the x through, I only have to do it twice because then I end up with additional terms that I no longer need. And then go ahead and distribute the x cubed over 6, and I only have to do that once in order to get these 3 non-zero terms. Well, how do we find the power series for tangent? Well, to do tangent, we do sine over cosine, and I'm only going to focus on the first 3 terms. So yes, we get the opportunity to do some long division, and I'm excited. I hope you are too. So I'm going to take my denominator into my numerator, and I say how many times does 1 go into x? It goes in x times. Multiply, and if you notice, I only want those 3 terms, so that when I subtract, I get this expression. Now, how many times does 1 go into 1/3 x cubed? It would be 1/3 x cubed times, and try to save yourself a little bit of work here, just because hopefully you know the long division well enough that after you do your subtraction, 1 goes into that, and I simplified it. So X plus 1/3 x cubed plus 2/15 x to the 5th. And so there are our first three non-zero terms. And if we really wanted to, we could write a rule for it, but no, we don't have to. So AP number 1, this AP style question says, this is the Taylor series for about 0, which means Maclaurin, for which of the following functions. Now, before I show you all the functions, you should be able to recognize what this one is. If you don't recognize it, that's fine. You could build the Taylor series, but I caution you, this is a non-calculator question, which means you have 2 minutes to do this non-calculator question. If you don't know the Taylor series, you'd have to build it. And which function are you going to build? Well, the function I'm going to build is going to be one of these functions. So how are we supposed to choose which function it is that we're going to build? That's a lot of individual work for just 2 minutes. Since we don't have 2 minutes, we really need to know what these series are. So which one does this model? Hopefully you know, but it's going to model this expression, but not alternating. So therefore, it is e to the negative x. For AP problem number 2, you see what that series, we're looking to see which one it is. So we need to know what the sine series is. And if you remember, the sine series of t is going to be t minus t cubed over 3 factorial plus t to the 5th over 5 factorial, et cetera, et cetera. But if we divide all of those by t, we're going to get answer choice A. Then we have our free response problem. When it comes to our free response problem, I left this blank because I wanted to work out all the details on this one together, just so you could see into the mentality of what it is that we're looking for. So we have our nth derivative given, so that's going to be important. We have our nth derivative given. We're told that we have a horizontal tangent, and we're told f of 0 is 6. So our first goal is to determine whether f has a relative maximum, a relative minimum, or neither. In order for us to have a relative maximum, minimum, or neither, what this kind of shouts out at me is our second derivative test. So with a flashback, that does say test, believe it or not, with our flashback to first semester, in order for us to have our second derivative test, we need to say f prime of x has to equal 0. So in this case, and then f double prime of x has to be positive or negative. Now, does f prime of x equal 0? Because if not, then it's going to be neither. So let's check. What is f prime of x? Are we given anything about f prime of x? Yes, we are. In fact, we are given that we have a horizontal tangent line. So because f has a horizontal tangent at x equals 0, we know that f prime of 0 equals 0. And now, what is f double prime? F double prime not of x, f double prime of 0 is going to be -1 to the 2 plus 1 power, so -1 cubed. And then we have 2 plus 1 or 3 factorial over 5. And I honestly don't know why I'm bothering writing this, because we want to know what the sign is. So 5 squared times 1 squared. So we know that this is less than 0. Therefore, we have a relative maximum. So we have relative max at x equals 0. I'm going to pause this for just one moment. All right, continuing on, our second task is we need to write the third degree Taylor polynomial. So in order for us to write the third degree Taylor polynomial, what we really need is, what is f of 0? What is f? And we know that one is 6. We need f prime of 0. And we just found out before that f prime of 0 does equal 0. We need to know f double prime of 0. So if we continued the work that we had there, f double prime of 0 ends up being -3 over 25, if I'm calculating it right. And now, how far do I need to go? I need a third degree Taylor polynomial. So what is our third derivative at 0? Our third derivative at 0 is going to be a positive. And that's because we have -1 to the 4th power. We will have 4 factorial over 5 to the third times 3 minus 1 squared, so times 4. So 4 factorial over 5 cubed times 4. We can simplify that. The 4s are going to reduce, so we have 3 times 2, which is 6 over 125. Moving right along. So that's 6 over 125. Let's put it all together. We have negative 3 over 25. I think we have everything that we need to go. So our Taylor polynomial, let's go ahead and call this P of x. I guess T of x would be appropriate since it's Taylor. So it doesn't matter what you call it, honestly. So T of x is going to equal our first term, which is 6, our second term, which is going to be 0. Doesn't matter what happens after that. Our third term is going to be negative 3 over 25 x squared. And then our fourth term is going to be it's going to be, actually, that should be 1 over 125. I think I didn't divide by 3 factorial. So in this case, the 2 factorial I had in there, negative 3/25. Then, so 1/25 x to the third. Sorry, I'm getting a little distracted over here. So Taylor polynomial. And that was because that was 6 over 125 over 3 factorial. So this should be negative 6 over 25 over 2 factorial. All right, moving on. Radius of convergence for our Taylor series. So in order for us to have our radius of convergence for our Taylor series, if you remember, we're going to have to take our limit as n approaches infinity. So limit as n approaches infinity of our next derivative's coefficient. So I'm going to move back up and say that it's going to be negative 1 to the n plus 2 times n plus 2 factorial over 5 to the n plus 1 times n squared. And that would be x to the n plus 1. Now we're going to multiply that by the reciprocal. So if we multiply that by the reciprocal, that would be 5 to the n minus 1 squared over negative 1 to the n plus 1 times n plus 1 factorial. And we need that limit to be less than 1. So if that limit is less than 1, then we will say a little bit simply, limit as n approaches infinity. We don't have to worry about the absolute value of the negative 1. So it's going to be the absolute value of n plus 2 is left in the numerator. The 5 is not going to be there anymore. The n minus 1 squared over, let's see, losing track of all my terms. This is gone. Then I probably shouldn't erase that. So we still have n squared. Yep, we still have n squared, and we still have a 5 here. This limit must be less than 1. So I feel like I'm missing one more term. So sorry about this for just 1 second. I'm missing an n. So I was missing an n, and I have a little bit of a typo. So that should be n plus 2. We have also, I'm missing, I have x to the n plus 1 over x to the n, so there's an x there. So we end up with, long story short, this limit ends up being 1. I know there's a little bit of typo here, but we have x over 5. Absolute value of x over 5 is less than 1. So the absolute value of x is less than 5. Therefore, our radius of convergence is 5. Just a little bit of keeping there that I need to do, but just wanted to cut to the chase right there. So sorry about that last problem, but everything else, okay. You guys have a great day.